here we have a spherical capacitor. The inner conductor has a radius of 1 meter and the outer conductor 1.01 meters. Half of the space between the plates is filled with the dielectric of permittivity 2 epsilon sub 0 and half with the dielectric of permittivity epsilon sub 0. So we want to find the capacitance of this structure. So we're going to apply a voltage to it like this between the two conductors and find the corresponding charge that will form on the conductors. Let me refer to the dielectric in the upper part of the capacitor as A and in the lower part of the capacitor as B. Now we know that the voltage drop across the capacitor is minus the integral from the outer conductor to the inner conductor of E dot dl. So integrating through dielectric B or through dielectric A has to result in the same potential because that is being set by the battery we're attaching to the capacitor. So to get the same electric field intensity profile in A and B means that there's going to be a higher density of free charge on the inner conductor in region B than on the inner conductor in region A, because material B will polarize more than material A will. So on the inner conductor in region A we have surface charge density rho sub SA, and on the inner conductor in the region of dielectric B the surface charge density is rho sub SB. So here we're looking at the lines of electric flux density in dielectric A and B, and because of the spherical symmetry of the capacitor, we know that these electric flux densities will have a spherical symmetry. They will only point in the A sub R direction and only depend on the component R. So in other words, D sub A will have the form a component only in the R direction, only depending on R, and for the electric flux density field in material B, it will also only have an R component depending only on R. So here I've drawn in a Gaussian surface that consists of a half of a sphere on this side, and this side is just a flat portion. So there is no electric flux going through this flat portion, and on this half a sphere we see that the electric flux density field is in the same direction as an outward normal everywhere on this portion of our Gaussian surface. So let's apply Gauss's law to this Gaussian surface. Okay, so D has the form D sub RB in the R direction, and the charge enclosed will be the surface charge density, or rho sub SB, times our area. So that will be this area, this half the surface area of the inner conductor, which would be 1/2 times 4 pi r squared, but r will be the radius of the inner conductor. So I can replace that with 1 meter squared. So D sub RB is constant everywhere on the surface here of our Gaussian surface. So we can take that to the left of the integral. And the dot product here just gives us the differential on the surface of our sphere. So this integral will give us the area of this spherical portion of our Gaussian surface. So that's half the area of a sphere of radius r. Solving, we obtain d sub rb is equal to rho sub sb over r squared. Similarly, we find d sub ra is equal to rho sub sa over r squared. Dividing our electric flux density fields by the permittivities in the two regions, we can get the electric field intensities in the two regions. The voltage between the two conductors is minus the integral of E dot dl from R equals 1.01 to R equals 1. Whether we integrate through material B or through material A, we have to get the same result. So you can conclude that rho sub SB over 2 must equal rho sub SA. Let's perform this integration to get the potential in terms of rho sub SA. The integral of dr over r squared is minus 1 over r. So here is the result of the integration, and our limits of integration are 1 and 1.01. So completing the integration, we get the potential across the two conductors is rho sub SA over epsilon sub 0 times 0.01. Now let's find the charge on our capacitor. The charge consists of the charge on the top half of the inner conductor plus the charge on the bottom half of the inner conductor. The charge on the top half is the charge density on the top half times half the area of a sphere of radius 1 meter. The charge on the bottom half is the surface charge density on the bottom half times half the surface area of a sphere of radius 1 meter. For rho sub SB, we will substitute 2 rho sub SA. So the total charge is 6 pi times rho sub SA. The capacitance is Q over V, and Q is 6 pi rho sub SA. And we found V earlier in terms of rho sub SA. So let's substitute that for our potential here. The rho sub SA's cancel, and we're left with 6 pi epsilon sub 0 times 10 to the second. Substituting for epsilon sub 0, 6 pi over 36 pi will leave us a 6 in the denominator. So we have 1/6 times 10 to the minus 7 farads, or 1.7 times 10 to the minus 8 farads.